All right, so this is one of the last slides that we looked at on our last lecture when we were talking about what a London force is, which is the weakest type of intermolecular force. London forces are also sometimes called induced dipole forces. Then we looked at dipole-dipole forces, which are present in molecules that have a permanent dipole. And then we looked at a special class of dipole-dipole forces that falls into its own category, and we call those hydrogen bonds. So it says a hydrogen bond is a special dipole-dipole interaction between the hydrogen atom of a lone pair, the hydrogen atom and a lone pair of electrons. It's important that when we represent hydrogen bonding, that we show it occurring between a hydrogen atom and a lone pair of electrons. And I'm going to show you on this slide how we represent that. And the hydrogen bond typically involves fluorine, oxygen, or nitrogen, and it has a moderate strength in between 10 to 40 kilojoules per mole. So when you look at a molecule and you're asking yourself, does this molecule have hydrogen bonding? You're going to have to either have a hydrogen bond to fluorine, oxygen, or nitrogen. Let me show you the hydrogen bond and how we would represent it in HF. Okay, here's hydrogen fluoride. Now, fluorine is the second most electronegative element in the periodic table, so it's going to be very delta negative, right? It's going to pull most of the electron density in this bond towards itself. It's hogging the electrons, so to speak. So it's going to be partially negative. It's not an anion, but it's got more partial negative character than hydrogen does, and that's going to render the hydrogen partially positive. If I draw a second molecule of HF, the way that we represent that, and I'll try to be color consistent here, the way that we draw the hydrogen bond is like this. Since we have a delta plus here and a delta minus here, it tells us that it's between a hydrogen atom and a lone pair. So we draw the hydrogen bond as a dashed line between the hydrogen atom and the lone pair, like that. Okay, that's how we represent the hydrogen bond. Again, which is just a special type of dipole-dipole. Notice that in an HF molecule, you've got one hydrogen atom, but you've got three pairs of electrons. If we look at ammonia and water, which are on the next slide, and we looked at this during the last lecture, you see that in water, we have two lone pairs and two hydrogens, right? Every water molecule has two lone pairs and two hydrogens. And so the hydrogen bonding is maximized in water. And that's one of the reasons why water has such a high boiling point, is because hydrogen bonding is completely maxed out. Whereas in ammonia, where again, we see the hydrogen bond being represented between the lone pair on the nitrogen of the ammonia molecule and the hydrogen of another ammonia molecule. Well, look at ammonia. Ammonia has one lone pair, but three hydrogens. And so the only case where every lone pair and every hydrogen atom can participate in a hydrogen bond is water. That's, again, one of the reasons why water has such a high boiling point. If we look at this figure here on this slide, and we just focus on hydrides of group 4A elements, as we go from methane to silicon tetrafluoride to germanium tetrafluoride to tin, or tetrahydride, silicon tetrahydride, germanium tetrahydride, and tin tetrahydride. What do we see? We see that boiling point, which is on the y-axis here, we see that it increases as we go from methane and we go down the group. Why is that? The reason why the boiling point is increasing is because the size of the molecules is getting bigger and bigger. As the size of the molecules gets larger, the polarizability of the molecule becomes greater. Remember, I talked about polarizability in our last lecture, and I said it's the ability of the electron cloud to distort, okay? And when a molecule becomes more polarizable, the intermolecular forces are going to be stronger. Now, what are the only intermolecular forces you would see in any of these molecules here? Since they're all tetrahedral, they're not going to be polar molecules. So it's only going to be London forces that these molecules will experience. And again, as the size increases, the intermolecular forces or the London forces will get stronger because the molecules become more polarizable. If we look at groups 5A, 6A, and 7A, you kind of see a similar trend, right? You see the trend increasing here, and increasing here. And all those red arrows that I have pointing upwards or having a positive slope, though the rationale as to why those boiling points increase are the exact same as what I just explained for group 4A. But you see that there's an anomaly in group 5A, ammonia. There's an anomaly here, water, and there's an anomaly here, which is HF. Well, if we compare the three of these, you see that water, you might think, why are they in this order? Well, the reason why water is the king of the castle and it has the highest boiling point of all of them is because hydrogen bonding is maximized in water, right? Completely maxed out. I've got 2 hydrogens and 2 lone pairs. So that's the maximum amount of hydrogen bonding that's possible. If I compare ammonia versus HF, the reason that HF has a higher boiling point than ammonia is simply because the fluorine is more electronegative. And so the bond is more polar. So the fluorine is more partially negative, and therefore it's going to attract a partial positive charge in the hydrogen with a greater strength than we would see in ammonia. And so you should know this order. Okay, I'm just going to say it in plain old English. Boiling point, you should know that water has a higher boiling point than HF, which has a higher boiling point than ammonia, and you should have an idea as to why. Okay, and the reasons are what I just explained. With that in mind, let's take a look at an example. It says, which has a higher boiling point, ethanol or dimethyl ether? So they give you the names and they also give you the structures. So the structures are shown here. So this is the structure of ethanol. This is the structure of dimethyl ether. And on top of that, they've given you some space filling models down here to look at. What do you notice first? First thing I notice is that they both have the same molar mass, don't they? Right? They both have the same molar mass, but obviously they probably have a different boiling point. I don't know. One of the answers is they have the same boiling point. Anyhow, what do you notice with these molecules? Let's look at ethanol first. Okay, let's look at it in gross and dirty detail. Okay, I'm going to ask my students, is there anything that my students notice with ethanol in terms of its intermolecular forces? What do you think the major intermolecular force would be in a molecule like ethanol? What do you think the strongest intermolecular force would be between 2 molecules of ethanol? What kind of interesting feature do you see in ethanol? Yeah, okay. I'd say the most prominent type of intermolecular force that you would see in ethanol would be hydrogen bonding. Remember, in order to have hydrogen bonding in a molecule, we've got to have either a bond to hydrogen and fluorine, hydrogen and nitrogen, or hydrogen and oxygen. And we have a bond between oxygen and hydrogen right here. So ethanol has, let me just write it like this, hydrogen bonding. Okay, is ethanol a polar molecule? The answer is yes, ethanol is a polar molecule. If we draw the Lewis structure of ethanol out, okay, and we look at the molecular geometry around the oxygen, it's got 2 bonds and 2 lone pairs. Therefore, I've got a dipole going this way and I've got a dipole going that way. So ethanol is a polar molecule. And so we could also add that it's got dipole as well. It also is a molecule that has electrons. So it's also going to have London forces. Okay, these are all of the intermolecular forces that 2 molecules or more of ethanol would experience with one another. What's the king of the castle? Hydrogen bonding is the strongest out of all of 3 of these. If I look at the structure of dimethyl ether, is there any hydrogen bonding present in dimethyl ether? What do you think? No, absolutely not. There is no hydrogen bonding. So there's no hydrogen bonding. Is there a dipole force in dimethyl ether? Look, you have to go back to Vesper, and you have to know that the molecular geometry on the oxygen in the middle is bent. Therefore, you're going to have a dipole going this way and a dipole going this way. And overall, the net dipole, or there will be a resultant or net dipole. And so it does have dipole interactions. And since it contains electrons, everything has London forces. Everything. You can always list London forces. Now, which one of these is the king of the castle for my dimethyl ether? The answer is going to be the dipole. But remember that hydrogen bonding is stronger than a dipole intermolecular force. And so the answer is ethanol is going to have the strongest intermolecular force, the hydrogen bond, and therefore it is going to have the higher boiling point of the two. Now, something that I haven't been talking about is the carbon-hydrogen bonds, right? There's CH3 here and CH3 here. There's a CH3 here. There's a CH2 there. Why did I leave out those bonds, right? Because this carbon is tetrahedral. This carbon is tetrahedral. But why did I leave all that stuff out? I'll tell you why, okay? The reason why is because carbon-hydrogen and carbon-carbon bonds, those are non-polar. Okay, so the only type of intermolecular force you'll ever experience in a portion of the molecule that contains just carbon and hydrogen will be London forces. That's it. Okay, give me a thumbs up if this makes some sense to you. All right, good. Again, you probably noticed that what we're talking about here is largely conceptual. If we look up the boiling point of ethanol, ethanol boils at 78 degrees Celsius, and dimethyl ether boils at minus 24 degrees Celsius. All right, well, let's move on from there. And look at a summary of all the intermolecular forces that we've looked at so far. This is it says qualitative summary 1. That would imply that I have more than one qualitative summary, and I'll show you what I mean by that in a little bit. All right, what do we have? The weakest of all the intermolecular forces are London forces, okay? So dispersion forces, this is the same thing as London forces, okay? It's the exact same thing, or dispersion forces. Sometimes we call them London dispersion forces. They all mean the exact same thing. They are present in everything. All molecules and atoms have London forces, okay? So you can always write that down as one of the intermolecular forces of everything, every molecule, every atom, okay? Remember, when you have a molecule or an atom that is nonpolar, you can get what's called a temporary or a fleeting or a momentary dipole, where let's say all of the electron density goes to one side of the molecule or atom. That's going to render the other side partially positive. And then that's going to cause an attraction between the partial positive and the electrons in the neighboring atom or molecule. So we call that an induced dipole. Okay, we can put that down here too. We'll put or induced dipole. Annoyed or what? Okay. In chemistry, sometimes we have a lot of ways to describe things. Anyhow, the next one is a dipole force. The only time you're going to find a dipole force would be when you have a polar molecule. Not necessarily a molecule with a polar bond, but an overall polar molecule. That's why it's important that you know your VSEPR, right? Valence shell electron pair repulsion theory. You know the shapes of molecules, and you're able to determine when a molecule is polar or not. Here we see a permanent dipole in a molecule, and that is going to be attracted to the permanent dipole in another molecule. And of course, the opposite charges or partial charges are going to attract. The next one is a hydrogen bond. A hydrogen bond is just a special type of dipole-dipole force, right? Water is a polar molecule. You know, HF is a polar molecule. Ammonia is a polar molecule. They all have polar bonds. But when we have hydrogen bonding, we have to have hydrogen bound to either fluorine or nitrogen or oxygen. Those are the only three atoms that meet the criteria. Chlorine, iodine, those don't meet the criteria. Okay, they are polar molecules, like HCl is a polar molecule, but the strength of the interaction between the delta negative on chlorine and the delta positive on the hydrogen of HCl would not fall under the category of the strength of hydrogen bonding. And then the very first one we actually looked at was the ion dipole. We said, why do ionic compounds solubilize so well in water? Why does sodium chloride dissolve in water? What makes the interaction of a sodium or a chloride ion with water so favorable? And it's the fact that there's two sides to a water molecule, right? The side with the oxygen is delta negative, but the sides with the hydrogen, that's delta positive. And so if the oxygens surround a cation, which is positive, they'll stabilize it. And if the other side surrounds an anion, they will, in fact, stabilize it. Give me a thumbs up if this summary helps to clarify things in your mind a little bit, or let me know if you have any questions. All right. Well, a couple more things before we can move on to the next slide, okay? First of all, the strength increases as we go from London to dipole to hydrogen bonding to ion dipole. Another thing I want to point out is if you look at all of these intermolecular forces, these all involve pure compounds. Pure compounds. Whereas the ion dipole involves a mixture, doesn't it? It involves an ionic compound or an ion in a polar solvent. Okay, it says here a mixture. Okay, so this is the only one that would be a mixture. Now here's a second qualitative summary. And you're like, well, Mr. Dion, why do you need two summaries? Well, the reason why is because it kind of threw in a couple extras here, okay? But if you understood what the heck was going on the last slide, you'll figure out what's going on in this slide. So here we have the strength reversed, okay? We have strength, generally speaking, where's my red pen? Strength is increasing this way, okay, generally speaking. And you can see that is characterized here in the amount of energy in these intermolecular forces. So we'll go from the top. We have the ion dipole, the hydrogen bond, and the dipole-dipole. We just covered those in gross and dirty detail. If you go way down to the bottom, you have the dispersion forces, which we call London forces or London dispersion forces. Then it kind of stuck to here down to the bottom. Okay, if we go up from the dispersion forces, what about a dipole and an induced dipole? Right? What if you have a polar molecule and a nonpolar molecule? Well, the polar molecule can induce a dipole, right? If you have if you have your partial negative on your polar molecule, it's going to repel the electrons in a nonpolar molecule and push them away. So you're going to get a delta plus. Okay. Now notice that that's only a little bit stronger than London forces. Whereas if we have an ion-induced dipole, since an ion has a greater charge than a dipole, which is just a partial charge, well, the ion-induced dipole works the exact same way, but it's going to be a little bit stronger. So one more thing I want to cover before I leave this slide, okay? And that's kind of like, the elephant in the room. It's this guy right here. Think about dispersion forces. What did I tell you about dispersion forces? I said they're the weakest, right? They're so weak. Oh, they're just so weak. Well, look at this. If you look at the range of dispersion forces, it goes all the way up to 40 kilojoules per mole. I mean, that's the top of the hydrogen bond. You're like, what the heck, man? What the heck? Well, if you're wondering, like, when would you see a London force that has a strength of like 40 kilojoules per mole? This would be with really, really huge nonpolar molecules, right? Molecules that are just so big, where the electron cloud is so big and so polarizable, so long. Remember my analogy that I used last lecture with the Velcro, right? If you have a molecule that's long enough and has enough of those weak forces, eventually they pile up into something big, right? Who was it that said everything big starts small? You know, was that Elon Musk? Anyhow, all right. Well, there you go. So that's another summary. And yeah, just gives you a little bit more insight on some other interactions you could have, namely the ion-induced dipole. I've shown one here between the iron 2+ ion and oxygen. So that's found in hemoglobin. And then the dipole. So there's a dipole in HCl, but there's no dipole in chlorine. And we went over that in some detail. All right. Give me a thumbs up if intermolecular forces are coming even more into focus, right? It always starts out kind of cloudy, and then it gets even more and more, you know, it kind of, the resolution gets better as we talk about it more and more. Great, good. Okay, remember, this is a very conceptual, you know, portion of our course. So if at any moment you want to stop me and ask a question, feel free to do that, okay? It's not, conceptual chemistry can be really difficult sometimes. Okay, let's try another question. Which one of the following is a liquid at room temperature? It says here one of them is a liquid at room temperature. Which one do you think it is? Okay, I'll give you a second to think about it. Yeah, thanks, Aurora. Yeah, somebody put an answer. So Aurora gave us an answer. She said, I think I got it. Aurora, can you tell me why you think hydrogen peroxide would have the higher boiling point? They all have the same, you know, approximate molar mass. They're not that far off. Yeah, exactly. So Aurora said, if I look at H2O2, hydrogen peroxide, you can see I have oxygen hydrogen bonds. So I could form hydrogen bonds. Okay. Whereas if I look at formaldehyde, there's a dipole in the molecule. So it has dipole-dipole forces. It also has London forces. Okay. But again, hydrogen peroxide has hydrogen bonding. It also has dipole forces. And it also has London forces. Now, why would H2O2 have dipole forces? Well, this is where your VSEPR theory comes in handy, because you know that each oxygen has 2 bonds and 2 lone pairs. And so it's going to be a polar molecule. Fluoromethane, on the other hand, if we draw fluoromethane, that's tetrahedral, right? If we draw fluoromethane, we have polar bonds, right? The carbon-fluorine bond is definitely a polar bond, but you've got 4 of them pulling in equal and opposite directions, right? I've got one here, I've got one here, I've got one here, and I've got one here. They're all pulling in equal and opposite directions of a tetrahedron. And so this is a nonpolar molecule. And so the only forces that fluoromethane is going to feel, oh shit, did I draw the wrong thing? Crap-a-doodle. I'm thinking of tetrafluoromethane. Sorry, you guys. Nobody stopped me, so I'll just erase all that. Sorry, fluoromethane is it is a polar molecule. Sorry, I had the wrong molecule in the brain. It's tetrafluoromethane, which is definitely polar. Okay, if I draw my hydrogen here and my hydrogen here, look. So I've got a polar bond going this way. Carbon is actually more electronegative than hydrogen, so overall there's a dipole with this molecule. So this molecule does have dipole forces, and it does have London forces. But again, I mean, Aurora answered the question really quickly, and she's 100% right that this is the only one that possesses hydrogen bonding. And so hydrogen peroxide is going to have the strongest intermolecular forces, and so it'll be a liquid at room temperature, whereas the other two will be gases at room temperature. Okay, these are both gases. Now, if you think, hey, in my biology class, I saw, something preserved in formaldehyde, and formaldehyde's a liquid. Well, that wasn't formaldehyde that you saw. Formaldehyde is a gas, and what you saw is a solution of formaldehyde in water, and that's actually called formalin. People just call it formaldehyde. Okay, well, I hope you're all with me a little bit. Let's take a deep breath here. That's a lot of talk about intermolecular forces. Look, I switched careers about 5 years ago. I started teaching full time. Before that, I was a medicinal chemist in the pharmaceutical industry most of my adult life. And, if I could describe my life now being a teacher to another person who's a chemistry teacher, I say this. I wake up in the morning, I brush my teeth, and I talk about intermolecular forces until it's time to go to bed. And that's what it feels like sometimes, because intermolecular forces, what we just covered, all these concepts here, these come up in general chemistry 1, in general chemistry 2, in biology, in biochemistry, in cell biology, in organic chemistry, in inorganic chemistry. I mean, they come up in every type of chemistry. So don't ever think you're like, I'll just, kind of skip this one. I'll slide past the intermolecular forces. I can't stress it enough how important intermolecular forces are that you understand. So if after all of my lecturing, and if you go back and you watch the videos, once, maybe twice, whatever, if you're still struggling, I would recommend looking at other resources, making sure you look at the textbook and read that thoroughly. Maybe she has a different way of explaining something that might help it crystallize in your mind. Another option would be to, and this is what I think is the best option, would be to do some practice problems. Go to the back of the book, find the questions that have the letter A next to them. That means you have the answer, and try as many of those problems as possible that deal with intermolecular forces. All right? But remember, before you can really tackle intermolecular forces and always be confident that you know what's going on, you really have to be, solid in your VSEPR, right? You've got to know valence shell electron pair repulsion theory, and you've got to know molecular geometry really well, because in order for you to tell when a molecule's got a dipole, right? You see dipoles come up here, they come up here. They come up in almost everything. You've got to be able to look at a molecule and say, hey, this is a polar molecule. Okay? You've got to be able to look at a molecule and say, it's not polar. Okay? All right. Somebody asked, will questions on the exams look like the one we just did on intermolecular forces? Yes, absolutely. Okay, they're definitely going to be in the same vein. Okay. How else? Where would be another good place to practice? Would be to look at the practice exam 3. Okay. Somebody says, I don't understand why fluoromethane doesn't have any hydrogen bonds, right? In fluoromethane, we have a fluorine atom, and we also have hydrogens, but they're not bound to each other. That is why whenever I listed the criteria, I drew a bond between hydrogen and fluorine. I drew a bond between hydrogen and oxygen. I drew a bond between hydrogen and nitrogen. You've got to have one of these bonds. If you don't have one of those bonds, you will not have hydrogen bonding. There is no bond between fluorine and hydrogen. There's a bond between fluorine and carbon. Okay, but there's no bond between fluorine and hydrogen. Does that help, Camden? Okay, good. All right. Look, if you want another example, look at formaldehyde. In formaldehyde, we have hydrogens, we have oxygens, but there's no hydrogen bonding, right? Because there's no hydrogen and oxygen bond. All right. Well, let's move on from there. And we're going to switch gears slightly here. We're going to talk about gases, liquids, and solids. What we're going to be talking about now is going to be largely conceptual. So keep an open mind and see if you can follow me. Okay. You can see this figure down here on the bottom of the slide. We got what? We got a solid. It's all neatly packed together here. Where's my highlighter? Got this beautiful solid here. Everything's neatly packed together. We heat that up. We provide more thermal energy to that solid. And what does it do? It leads to a phase change. It goes from a solid to a liquid, right? You provide more thermal energy, all of a sudden the particles start vibrating, they're moving, and then what happens is that the attractive forces in the solid are overcome by that increased kinetic energy, and you make a liquid. Are there forces holding the molecules in a liquid together? Absolutely. Right, but what do we know about a liquid? If you heat it more and more and more, you provide more thermal energy, the molecules or atoms are going to start moving faster and faster and faster and faster and faster and faster. And once they have enough kinetic energy, the intermolecular forces that hold the molecules or atoms together in a liquid are going to break apart, and you're going to end up forming a gas. Right? The opposite is true if we remove thermal energy, right? If we cool the mixture, if we cool the gas, it's going to condense to form a liquid. And if we cool that liquid even further, it's going to freeze to give us a solid. Again, what am I trying to get at here? Why are we talking about gases, liquids, and solids, which is something we talked about at the very beginning of this class? Why are we discussing it in this chapter? Because you need to understand the attractive forces, right? What are the forces of attraction between particles of matter? Intermolecular forces. So depending on the solid, maybe it's hydrogen bonds that need to be overcome. Maybe it's a dipole force that needs to be overcome. If it's a polar molecule, if it's a non-polar molecule, then it's going to be London forces that need to be overcome in order to convert it from a solid to a liquid. Okay, that's the kind of mindset you want to keep while we're progressing through the material. Well, let's talk about vaporization. You're all aware of what vaporization is. If any of you have ever had a cold before, maybe you had a parent or a loved one who took care of you and put a vaporizer in your room. I don't know if you've ever heard of a vaporizer even, but in Canada they're popular because people have colds all the time up there, right? And we take a vaporizer, which basically you just put some water in it and it heats up the water, and then you can put Vicks Vapor Rub or something in it anyhow, and it makes some it puts some I don't know, what's the word I'm looking for? I can't think of it right now, but anyhow, it puts vapor in the air and makes it easier to breathe, and you're not as dry. Anyhow, but I'm making something simple really complicated. What's vaporization? It says here, in a liquid, the average kinetic energy of the molecules is going to be proportional to temperature, right? That's the distribution of kinetic energies. Remember, we looked at that, the Boltzmann distribution. This is something that we looked at quite a while ago in the class. If we draw, a curve here, let me do my best here. That's not very straight, is it? We draw a curve. If on the x-axis we put the speed of our molecules, and then over here we put the number of, we'll put number of particles because it could be an atom, okay? Well, let's say we have a temperature. Let me use a different color. What if we have a temperature and we have a distribution that looks like this? Okay, and then we increase the temperature. What does it do? It flattens the curve, but then we have a greater number of, that looks like crap. And we have a greater number of molecules with increased kinetic energy, like that. So here we would say that if we called this one, we'll call this T2, and we'll call this T1. So then we'd say T2 is greater than T1. Anyhow, that's the Boltzmann distribution, and we looked at it earlier. But what's the idea here? This is the distribution of kinetic energies. And so you can see that as the temperature increases, we have a greater chunk of molecules, right, with greater kinetic energy. So some surface molecules have sufficient kinetic energy to overcome the intermolecular forces and escape the liquid to the gas phase. But we know that that kinetic energy, what I'm getting at here, is proportional to the temperature. As we increase the temperature, the kinetic energy of the molecules at the surface is going to be greater and greater and greater, until if we get to a high enough temperature that's called the boiling point, then all of the molecules, whether they're in the liquid or the gas phase, are going to have enough, all of the molecules in the gas phase are going to have enough kinetic energy to escape into the gaseous phase. So vaporization is the transition from a liquid to a gas. And evaporation is the word that we use for vaporization that occurs at temperatures lower than the boiling point. Okay, let me just kind of stop here and stop reading the slide and just kind of talk about what the heck is going on. If you you know, put your face over top of a glass of water. Forgive me. How do you draw a person? I don't know, like this. Okay. Son of a gun. My person's going to be deleted, aren't they? No, they're not. They're still there. Okay, so if you have a person, okay, a person looking over top of a glass, he's not really looking in the right place, is he? Let me fix his eyeball. Okay, he should be looking down. No, I erased his eyeball. Son of a gun. I'm really struggling here. There we go. Okay, so the person's looking at the water. Okay, imagine that's you. Can you imagine being that lucky? Okay, and you're looking over a glass of water at 25 degrees Celsius, room temperature approximately. Do you feel water vapor pushing against your face? Well, the answer should be no, okay? I could do a demo, but I won't. If you take a glass of water and stick your face over top of it, you're not going to feel any water molecules like rushing into your face. Are there water molecules that are escaping from the liquid into the gaseous phase even though you don't detect it? Of course. How do you know? Let's say you take a glass of water and you leave it on your desk overnight or for a couple of days. You're the kind of person that doesn't like to do dishes. If you come back after a couple of days, will the volume or the level of the water, will it have decreased? The answer is yes. Not a lot. Did you boil it? No. But so that tells you that even at a low temperature, that's not the boiling point, some of the molecules at the surface are going to have enough kinetic energy to escape the liquid phase and go into the gaseous phase. Again, it's not a lot, but some will. Okay. What's the whole point of this slide? Is it's telling you that once you reach the boiling point, okay, since kinetic energy is connected to temperature, as you increase the temperature, more and more molecules are going to have enough kinetic energy to go from the liquid phase to the gas phase. And that's why when you're boiling water, you can feel the steam against your face, right? So the second point of your question, Blake, is not true. So you're saying here, how do more particles become fast as some leave without increasing the temperature? More particles do not get increasing kinetic energy. The distribution of T1 always remains the same, okay? There's always going to be some molecules that are going to have enough kinetic energy to escape into the gaseous phase, okay? But what happens, Blake, is I see what you're getting at. If they escape into the gaseous phase, why don't they just start condensing back into the glass? Well, the reason why condensation doesn't occur at the same rate is because where are the molecules going to go? When they evaporate, they go anywhere into the room, so they're not going to condense back into the glass. Does that make sense? Says, why does all the water escape eventually and not just the fast particles? Because you're always going to have some of the water that's going to possess enough kinetic energy to overcome the intermolecular forces. You'll always have a small subset that's going to be in here, right? That's going to have enough kinetic energy to escape into the gaseous phase. So the weaker the intermolecular attractive forces between molecules in the liquid phase, the faster the rate of vaporization. Less kinetic energy is going to be required to overcome those attractive forces. Let's think about a couple of liquids. Now, I've taught chemistry long enough to know not to ask my students about lantern fuel. Okay, but if you've ever seen nail polish remover, okay, so nail polish remover. Okay, if you spill a puddle or make a puddle of nail polish remover, right, it's going to evaporate really quickly. You're going to see it evaporate really, really quickly. Whereas if you spill some water, okay, the same amount of water, it's going to evaporate, right, but it's much slower. Why? Because the intermolecular forces that hold water molecules together, the hydrogen bond, are stronger than the intermolecular forces that hold nail polish remover together. All right. It says here that process, vaporization, is an endothermic process, right? Because you have to impart thermal energy into the molecules in order for them to overcome the attractive forces between them. The heat of vaporization, which we abbreviate as delta H, of vaporization is the amount of thermal energy that's required to vaporize 1 mole of a liquid. Remember though, Blake, as these particles leave, other particles are going to come in and take their place, right? Let's say the area under this curve here represents all of the molecules. What if you have less molecules? The curve still stands, okay? You'd still have the same curve. It's just going to be smaller, is all. It would have the exact same shape. It's just less. There's just going to be less molecules. So there will always be some molecules that possess a higher than average kinetic energy. All right. So the heat of vaporization is a definition you need to know. It's the amount of thermal energy required to vaporize 1 mole of a liquid. We go from the liquid phase to the gaseous phase. Okay. Well, this is getting back to Blake's point a little bit here about condensation. He said, well, if you have evaporation, you know, if you leave the glass out and you're saying that water molecules can escape from the liquid phase into the gaseous phase, why don't the gaseous molecules just condense at the same rate back into the glass? Well, the answer is the reason why is because in an open container, the vaporization is always or almost always going to occur at a greater rate than condensation. Why? Because again, the particles are going to go anywhere in the room and they're not just going to stay right above the glass and then condense back in like that. They're going to condense all over the place. Now, if we go back to the top, it says condensation occurs when vapor molecules lose kinetic energy and are captured by the liquid upon collision with the surface. Vaporization and condensation are opposite processes. Condensation is an exothermic process, right? If I look at delta H of condensation, it's the negative of the delta H of my vaporization. And so it is exothermic. Heat will be released. You know this if you've ever had steam come into contact with your skin. If anybody's ever been burned by steam, what happens when the steam hits your skin? Not only does it condense the water, but it releases a ton of heat. Okay, and that's why steam causes such bad burns. So somebody says, if it's a closed container, would it go back into the glass? That brings me to a good segue, Violet. So here we go. If we did have a closed container, so here we have an Erlenmeyer flask with a stopper in the top, eventually the rate of evaporization is going to be equal to the rate of condensation, and we call that a dynamic equilibrium. Here's an example shown at the bottom of the page, and this is bromine. This is bromine in the gaseous phase, and this is bromine in the liquid phase here. If we were to all get together as a class, coronavirus vaccine is, out there and it's working. We're all together and we're all standing around this bromine. Like, let's just spend a day looking at the bromine, okay? If we were looking at this with our eyeball, okay, it would look like nothing is happening. Is that true? No. We know that something is happening. The rate of evaporation of bromine is eventually going to equal the rate of condensation of the bromine in the liquid and gas phase, respectively. Okay? Both processes are still occurring, but there's going to be no net gain or loss of liquid or vapor. Okay? All right, so that's a dynamic equilibrium, and that is in a closed system. Well, if I started this whole experiment that's shown here at the top, if I started this and I had this empty, okay, if that was a vacuum, okay, no gas particles in there at all. Well, you can see that some gas particles are going to start pushing against the walls of the container, and eventually an equilibrium is reached. The pressure exerted by the molecules in the gaseous phase here, the pressure that they exert, okay, their pressure, this is called vapor pressure. It's the pressure exerted by the gaseous molecules above the liquid when the vapor and the liquid are in dynamic equilibrium. And it can be measured using a manometer. We spoke about those in the gas chapter, the ideal gases chapter. So we have some mercury in a tube here in our manometer. And then if we measure the difference in the height of the two columns of mercury in millimeters of mercury, that correlates with our vapor pressure. So you can imagine that the lower boiling point a liquid has, the more molecules you're going to have in a gas phase. What's pressure going to be related to? Pressure is proportional to the number of molecules. And so the more molecules that you have in the gaseous phase, the greater the vapor pressure is going to be. Okay? Vapor pressure is something I use all the time in my everyday speech. Okay, I'll give you an example of how you use it. If you're the kind of person like me who loses things around the house all the time, is anybody like me loses stuff around the house? Like I'll lose my hat or I lose my glasses. I don't know, I lose my phone. Okay. What I always tell my wife is I said, oh, I lost this, I lost this tape measure. It must have a high vapor pressure. What does a high vapor pressure mean? It means that the molecules are really wanting to go from the liquid phase into the gaseous phase. So it's another way of saying if something has a high vapor pressure, it evaporates quickly. So basically all the things that I lose, they just evaporate, they just go into the gaseous phase and we never find them again. All right, so vapor pressure. If we go all the way back here, where was my person that I drew? I can't do all that work and only use it once. Okay, so there's a certain amount of pressure, okay, of the water molecules pushing against the person's face. It's not big, they don't even notice it. But if you put your face over a puddle of, acetone, which is nail polish remover, you're going to smell the fumes, okay? Really strong because that molecule or that liquid has a higher vapor pressure because the intermolecular forces that hold molecules of nail polish remover together are only dipole forces, which are weaker than hydrogen bonds. I hope this is making some sense. I know I'm jumping around quite a bit, but I really want to try to drive these points home with you. And I don't want you to walk out of the lecture and be like, well, I didn't follow any of that. I want you to have some idea of what's going on. Okay? Look. You guys see this? A vintage Coke can. It's like so hard you can't even bend it when you squeeze it. Anyhow, this is a vintage Coke can. There's nothing in it. But imagine I had water in here, right? And I put my face over top of it like this. Are some of the molecules escaping phase and going into the gaseous phase? Absolutely. Do I detect it? No. But if I have a liquid that's got a higher vapor pressure, like, has anybody ever spilled lantern fuel before? I always ask this and I always get shut down by my students. They're like, I've never even heard of lantern fuel. Has anybody here ever bought Coleman fuel before? You guys know what Coleman fuel is? You can buy it at Walmart. It's in the camping section. Please tell. Okay, Christian, I got one person in the history of chemistry that's used lantern fuel. All right. Well, lantern fuel is mostly a hydrocarbon. Okay. So it's the only intermolecular forces in lantern fuel are London forces. Christian or Ashland Christian or Ashland. So I got two people. If you spill lantern fuel, has anybody, Christian or Ashland, have either of you spilled lantern fuel before? Like, whoa, just by accident, spilled a little on a picnic table or something? Anyhow, if you spill lantern fuel, and I'm not going to do a demo in my own house because I have some in a closet here, but I use it for a stove that I have. But it evaporates like that. It's gone. In a few seconds, you can just watch it go, watch it. You don't actually see the molecules, but you can watch the liquid, the puddle just shrinks and then it's gone. Okay? That has a really high vapor pressure. Does that make sense? Okay, what about propane? Has anybody here ever filled up a propane tank? You go to, I don't know, Home Depot or something, and you buy a propane tank. Has anybody here ever shaken a big barbecue propane tank before? I don't know, maybe I live a different life than you guys, but if you shake a propane tank, you'll actually hear inside the propane tank, it's liquid. Okay, it's liquid under that. Now, the reason why it's liquid is because it's under high pressure. What happens when you open that propane tank? Is it a liquid then? No. it goes into the gaseous phase like that, right? Because its vapor pressure is so high. Does that help? Yeah, so that's what happens. Okay, let me tell you one more quick story here. Son of a gun. I have all these things pop up in my. So let me tell you a story. Okay, I don't do this kind of stuff very often since I started teaching since coronavirus, but I like to tell stories in my class that are chemistry related. Anyhow, so I went to university with a guy who grew up in Saskatchewan, in northern Saskatchewan, super duper cold. And he told us, oh, a great story one time. We were sitting around in the chemistry learning center. He said that when he was a child, in the wintertime, he said that he remembers his father woke the family up and took them out into the barn on a cold winter's night. He said he took us all out of the house and put us in the barn and wrapped us up in blankets. And he said that he was really young. And he said, I didn't understand why my father was taking us out of the house. And he said, I remember my father saying to my mother, the propane is boiling. So, can anybody explain what he meant by that? He said, the propane is boiling, and he took the family out of the house and put them into the barn. Well, in the interest of time, I'll explain what he meant. The boiling point of propane is minus 42 degrees Celsius. That is really, really, really extremely cold. Okay, so that's why when you go to barbecue outside in Colorado, you can go out here on the coldest winter day and open up your barbecue, and you're still going to be able to barbecue because it's never going to reach minus 42 degrees Celsius. The thing is, where he lived in northern Saskatchewan, it was colder than minus 42 degrees Celsius. And so the propane that they used to heat the house, it was in the liquid phase, and there was none. As soon as they opened it up, it stayed a liquid. It didn't even have enough pressure, vapor pressure, to go into the pipes and to ignite. It's crazy. That's insane. You know, when you think about it, how cold that must have been. But does that make some sense? The propane is boiling, right? The vapor pressure is so low that there's no gas going up through the gas lines to light up the furnace. Anyhow, where was I? It is terrifying. I don't even want to live. I don't want to live there. You know, anybody feel like going on vacay to Saskatchewan? Probably not. Okay, now where the heck was I? I was here on vapor pressure. Okay, so vapor pressure is a characteristic of a substance at a given temperature, and it's going to be dependent on what? The magnitude of the intermolecular forces. I'll tell you right now, propane, the only intermolecular forces experienced by propane are London forces. It's a nonpolar molecule. Substances with smaller or lower intermolecular forces have higher vapor pressures. A substance with a higher vapor pressure, we call it volatile. Has anybody ever heard of the word volatile being used in their everyday life? Okay. Like when people use the word volatile in everyday life, a lot of times if you listen to the police, scanner or something, they use it to describe, people. Camden says they use it to describe the stock market. Absolutely, Camden. Right. What does it mean? It's unpredictable. Right. It's got a low boiling point. It's going crazy. Okay. So when something is volatile, the molecules are going crazy. They're in the gaseous phase. They have a lot of kinetic energy. So it's something that evaporates quickly. It's something that's volatile. And of course, volatility is going to vary with temperature. Anyhow, let's get to it here. Let's try a pop-up question. It says here, which of the following is the correct arrangement by increasing vapor pressure at minus 70 degrees Celsius? So remember, we're at 70 degrees Celsius. If we compare these three molecules, H2S, okay, we have three molecules. We've got H2S, we got HF, and we've got NH3, ammonia. Hydrogen sulfide, hydrogen fluoride, and ammonia. Well, if we compare these three molecules, these two have hydrogen bonding. Okay, H2S is a polar molecule, isn't it? We draw out the structure of H2S. It has a bent geometry, and so it is polar. And so it only has dipole-dipole forces. It has London forces too, but the strongest forces will be dipole forces. And so since it has the weakest intermolecular force, it's going to be the most volatile. So that means either B or D has to be the correct answer. Now, in terms of HF and NH3, we already looked at these earlier today, and I told you that you had to know that in terms of boiling point, water has the highest boiling point, HF has the next highest boiling point, and then ammonia is going to have the lower of those three. We looked at that on a figure earlier today. And so if I look at these, that means that HF, if I compare HF and NH3, HF is going to have the highest boiling point, and so it's going to have the lowest vapor pressure at minus 70 degrees Celsius. And so my answer is D. Now, if I make a plot of the relationship between vapor pressure and temperature, it'll look something like this. That's shown in this figure here. Here I have the vapor pressure on the y-axis, and I have the temperature on the x-axis. The higher the temperature, the higher the vapor pressure of a liquid, right? If I have water at 0 degrees Celsius, which is 273, and at 1 atmosphere, it's going to be a solid, right? It's going to have no vapor pressure if it's at 0 degrees Celsius. Okay, it's just a solid chunk of ice. Okay, but once we get up to around what? 1 atmosphere and 373 Kelvin, okay, then we reach the boiling point of water. So this is the boiling point of water. And you can see that it's got a much higher vapor pressure. Okay, it's going to have a pressure of around 760 millimeters of mercury. So if this is 1 atmosphere here, this line is 1 atmosphere. You can see the boiling point of ether is here, the boiling point of ethanol is here, and the boiling point of water is here. So we can find the boiling points of all of these. But the point behind this graph, what I really wanted to get at, is that if you look at the relationship between vapor pressure and temperature, it's nonlinear, isn't it? They all have a curve, right? This one's got a curve, this one's got a curve, so on and so forth. So nonlinear relationship. But what you find is if you plot the natural logarithm of the pressure versus 1 over temperature, you end up with a linear plot. Exponential plots like these, they make predictions really difficult, don't they? But linear relationships make predicting things a lot simpler. And so we're going to look now at the plot of the ln, or the natural logarithm of the vapor pressure versus 1 over temperature. And in the first figure here, I have that plot of pressure versus temperature, the nonlinear plot. And here I have the plot of the ln of the pressure and the reciprocal of the temperature. It says here that a plot of the natural logarithm of the vapor pressure versus the reciprocal of the absolute temperature. And if we get an equation for this line here, it is the ln of P is equal to minus the delta H of vaporization divided by RT plus B. You can see our B, our y-intercept is up here. And so if we have our pressure and our temperature and our y-intercept, we can determine the heat of vaporization. But what about if we had 2 points, right? It's going to be much more useful to use this equation in a 2-point form, right? If I had any 2 points along this line, then I could rearrange this equation to a 2-point form. I'll provide you with this equation for your last exam. If I do a 2-point version of that equation, which is useful for when I have 2 pressures and 2 temperatures, I get this equation that's called the Clausius-Clapeyron equation. Okay, notice that since my R is in joules per mole Kelvin, that my temperatures have to be in Kelvin. And then my delta H of vaporization is going to end up being in joules. You can pick P1 and P2, but just be consistent with the temperatures associated with each pressure. This applies when you're reading your values directly from a graph. So again, for the third exam, I will provide this equation. I will give this equation. Don't have to memorize the Clausius-Clapeyron equation. If you want to try deriving it from this formula using two pressures and two temperatures, be my guest. No problem at all. We don't do that in this class. But you're going to use the Clausius-Clapeyron equation in Gen Chem 2, so it might be something that's exciting to do. Anyhow, let's try a problem that employs the Clausius-Clapeyron equation. Oops. Sorry, I got a bit of a mess here on my desk. I'm trying to find the rest of me notes. Anyhow, I'll give you a second to look at the problem. It says the altitude in Colorado Springs is around 6,035 feet above sea level with an atmospheric pressure of 603 millimeters of mercury. At what temperature does water boil here? And it gives you the delta H of vaporization. All right. So let's see, what do we have here? We have Clausius-Clapeyron equation. I'll write it down. So it's the natural logarithm of P2 over P1 is equal to delta H of vaporization over R multiplied by 1 over T1 divided by 1 over, subtract 1 over T2. Okay, so let's start with our initial pressure. So our P1 is equal to, I'm going to choose atmospheric pressure. And for P2, I'll choose the pressure in Colorado Springs, which is 603 millimeters of mercury. Our T2 is what we're looking for, the boiling point of water in Colorado Springs. But we know that at 760 millimeters of mercury, that the boiling point of water is exactly 100 degrees Celsius. So you would have had to know that water boils at 100 degrees Celsius at atmospheric pressure in order to solve this problem. So then we could just plug some numbers into our equation. So let's try that. So we're going to take the natural logarithm of 603 divided by 760. I'm going to leave the units out because they're going to cancel anyway. Is equal to the heat of vaporization. Notice that it's in kilojoules. Since our R is 8.314 joules per Kelvin mole, we're going to have to convert this into joules. So we'll have to multiply by 1,000 joules in a kilojoule. So I'll write it like this. I'll put 40.7. Sort of a shorthand or a trick to do this is just write times 10 to the 3 joules per mole divided by 8.314 joules per Kelvin mole. And then I'm going to multiply that by 1 over T1. So 1 over 100 degrees Celsius. Remember, temperature has to be in Kelvin. So that's 373 Kelvin. So I'll put 1 over 373 Kelvin. Subtract 1 over X. Like that. Now I've already gone ahead and done some of the math here. You end up with negative 0. Let me just double check my math here. 603 divided by 760. Here's the long button. There we go. So you get negative 0.2314. I'm going to carry an extra sig fig here and I'll round off at the end, is equal to 4,895. Notice that joules cancel and moles cancel. So I get reciprocal Kelvin. And then I get 1 over 373K. So yeah, so I'll put 1 over 373 Kelvin, subtract 1 over X. Okay, then I simplified that a little bit further. And what did I do next? I just divided negative 0.2314 by 4,895. So you get negative 4.727 times 10 to the negative fifth Kelvin is equal to 1 over 73 Kelvin, subtract 1 over X, like that. So then you end up with, we go up here. There we go. So then you end up with negative 4.727 times 10 to the negative fifth plus 1 over X is equal to 2.68. Negative 3. Then you end up with 1 over X is equal to 2.727 times 10 to the negative 3 Kelvin to the minus 1. And then you get the X is equal to, I got 366.7 Kelvin. So then if I subtract 273 Kelvin, I get the X is equal to 93.7 degrees Celsius. Pretty close to that. Now I kind of went through this step by step by step, but I find it's kind of easier to work out the Clausius-Clapeyron equation this way. If you did it way faster than me, then no problem, as long as you get the right answer. But sometimes I like to work out all the algebra here just to kind of walk my students through it. All right. So what I want you to do before the next lecture is I want you to try pop-up question 12.6, which is the vapor pressure of chloroform is 400 torr at 24.1 degrees Celsius and 100 torr at minus 6.3. And you're going to solve the Clausius-Clapeyron equation for the delta H of vaporization.